Let's have a look at the 2024 Higher Level Maths Leaving Cert Paper 1, and this is question 3. So part A, we've got to integrate cos 6x. So let's do that. We've got to integrate cos 6x with respect to x. Well, if we integrate cos, we'll get sine 6x. But if you think about it, if we were to work backwards and differentiate, if we were to differentiate this, will we end up with this? Well, if we differentiate sine 6x, we'll get cos 6x all multiplied by 6, because you've got to differentiate the 6x as well by the chain rule. So we'll end up with an extra 6, which we don't want. So what we're going to do is put in a 1 over 6 here. So now if we differentiate this, we'll get 1/6 times 6 cos 6x. So the 1/6 and the 6 will cancel, and we'll just end up with cos 6x. And we need to remember to put in the c as well, the constant of integration. And that's it for part A. Let's have a look at part B. The function f is defined for f of x is equal to 2x cubed minus 9x squared plus 5x minus 11. Find the equation of the tangent to the graph of f at the point where x is equal to 2, and we don't need to simplify our answer. Okay, so the tangent is going to have an equation y minus y1 is equal to m into x minus x1. It's the equation of a straight line. Tangent is a straight line. So in order to complete this question, we need to find the slope, and we need to find our x1, y1, a point on the tangent. So let's find the slope first. So we have f of x is equal to 2x cubed minus 9x squared plus 5x minus 11. We want to differentiate. So we have 6x squared minus 2 9's 18, x plus 5. This is the slope of all the tangents at any point x on our curve. Now we want to find the slope of the tangent where x is equal to 2. So the slope at x is equal to 2 will be 6 times 2 squared minus 18 times 2 plus 5. When you do that, you get minus 7. You get minus 7. Okay, so that's the slope of our tangent. Now the other thing we need is we need a y1 and x1. Well, our x1 is going to be 2, so we need to work out what y would be when x is 2. So what we need to do is put that into our original function. So let's do that. So we have y value is going to be equal to 2 times 2 cubed minus 9 times 2 squared plus 5 times 2, and then we've got to subtract 11. So when you do all of that, you get minus 21. So that's our y value. So we have our x, our y, and our slope. So let's just slot those into our equation. So it's y minus y1, y minus y1, so it's y minus minus 21, which is plus 21, is equal to m, which is minus 7, times x minus our x1, which was plus 2. So that's really it. It says we don't have to simplify our answer. However, if you do decide to simplify it, you should end up with, let's see, y plus 21 is equal to minus 7x plus 14. Now just come up here, bring this 7x over, plus y, and then we've got plus 21 minus 14. That's going to give us plus 7 equal to 0. So this is the simplified version. They'll accept that answer because they say that you don't have to simplify. Okay, let's move on to part 2. Find the x-coordinate of the point of inflection of f. To find the point of inflection, we've got to differentiate twice. So from the previous question, we know that f prime x, the first differential, is 6x squared minus 18x plus 5. So let's differentiate again. So that's f double prime x is equal to 12x minus 18. So that's the second differential. What we need to do is let that equal to 0. So it's 12x minus 18 equal to 0. That'll give us 12x is equal to 18, or just x is equal to 18 over 12, which is 3 over 2, or 1.5. Now the question is, find the x-coordinate of the point of inflection. So we don't have to worry about finding the y-coordinate, so that's our answer there. Okay, so next question. Part C, the diagram below shows the curve y is equal to p of x and the line y is equal to L of x for x between 0 and 10. X is real. There are two values of x in the domain 0 to 10 for which the derivative of p is equal to the derivative of L. Use the information in the diagram to estimate these two values of x as accurately as you can. Show your work on the diagram. Okay, so what we do when we differentiate is we find the slope. Really the slope of the tangent to L is just the line L itself, if you like. So we want to find tangents on P that are the same, that have the same slope as L. So they're going to be two. One is going to be here, one is going to be there, and one is going to be roughly there like that. So that's where the tangents on P have the same slope as the tangent, if you like, of L, or the same slope as L. So this here is going to be, looks like about 6.9, and here we've got about, I think, 2.1. So my answer here would be x is equal to 2.1 and x is equal to 6.9. Okay, another way of looking at this might be to look at plotting the derivatives of both of these functions. If we take the straight line, for example, we've got a slope of, we can work out the slope easily enough. We take that there, that's 2 units. We work along here. We look at this triangle here, that's 6 to 10, which is 4 units. So the slope of our line is going to be 2 over 4. So the slope of y is equal to L of x is a half. If we were to plot that or draw that, we would be looking at drawing a line and that's the line y is equal to a half. Now drawing the, or sketching I should say rather than drawing, the derivative of p of x is going to be a little bit trickier I think, but let's have a look. We have a zero slope tangent here. If we were to draw a tangent here, there would be a zero slope for that tangent, and if we were to plot that, we would just plot it here. Same up here. If we were to take this point up here, that's roughly where there would be a zero slope tangent. We come down along here, we could plot that point there. Now the point of inflection is a little bit trickier. Let's see, we have the point of inflection is roughly around here, and the slope of the tangents around that would be, let's see, if we take a straight line down along here like this, we could say, let's see, if we take a triangle down along here, and here you would be looking at maybe 2.4 here, 2.4, and about 1.6 maybe here. So the slope there would be 2.4 over 1.6. That would be 1.5, a slope of 1.5, 1.5. Now that's fairly approximate, but if we were to plot that at the point of inflection 1.5, we would be looking at a point somewhere here. Now if we were to draw that, then be looking at coming up along here, come around here, and then back down along here. A little bit shaky there, but the points where the two derivatives intersect would be here and here. So we would be looking at about 2.1 and about 7.2. So different from our first estimates, 2.1 and 6.9 we got. Well, 2.1 is fine, 6.9 actually not too far away. This one here is a little bit different, alright. So we got 2.1 in both cases and 6.9 and 7.2 in the second case. That would be, there are two methods possibly of doing that particular question. Okay, and that's it for this question.